Our first talk this afternoon is by Elias Khalil from University of Toronto. Thanks for being here.
Okay, thanks, Robert, and thanks to the organizers for the invitation to speak here. I'm very happy to be joining you here as part of the program. So today I'm going to talk about some kind of late-breaking / ongoing work on the problem of finding backdoors in integer programs, and this is joint work with Pashtutan Faizepour in CS at the University of Toronto and Abisra Dilkina in CS at USC. Okay, so as with many of the talks, we'll be operating within the branch and bound scheme for integer programming. So without going into too many details, there's only a few that I care about that I'm going to highlight in particular that are relevant to this talk. So typical steps is selecting a node, solving its linear programming relaxation, which gives us a lower bound for the minimization problem, deciding whether we should prune that node based on the bound if we have a existing integer solution or upper cutoff, maybe adding some cuts. These may be local cuts further down in the tree, and then running primal heuristics to help us find feasible solutions. And last but not least, branching and splitting the subproblem into two new ones and going forward with this kind of divide and conquer scheme. Okay, the focus on this talk is going to be mostly within the branching realm, but this notion of backdoors that I'm going to revisit also affects other parts of these 6 steps. Particularly, there are some interactions with other solver components, for example, heuristics or cuts that are local to nodes of the branch and bound tree. Okay, so after we branch, we get a new node, we select it, and so on and so forth. And at any point in time, if you listened into Gregor's talk yesterday about estimating tree size, you have some potentially partial branch and bound tree. Okay, so the notion of backdoor for integer programs was defined in this paper by Dilkina et al. More than a decade ago now. And it says the following: if you have a problem, say in this case, a binary problem where there's many more variables than 3, and you do a bunch of branching on 3 variables, x1, x2, and x4. So if you look at all these edges, you'll only find these 3 variables. And after branching, if you look at your frontier of nodes and find that all of the nodes are fathomed or integer feasible, so maybe the green one is an integer feasible linear programming relaxation, the red X's are fathomed by bound, the orange one is maybe just an infeasible node LP, then you have a certificate tree, you're done, right? But you've only branched on 3 variables, okay? Even though there are potentially many more variables to this problem, okay? So this defines this notion of backdoor. Initially, this was introduced in the context of satisfiability, and people kind of used it as a way to quantify some notion of intrinsic complexity of these hard combinatorial problems. And you can imagine also using, you know, the existence of a backdoor to do some kind of fixed parameter tractability and say, you know, if there's a small backdoor, I can solve this problem more efficiently than if there isn't. So in MIP, things are a bit more interesting than in SAT, naturally, as we all know and agree. And there's this interaction between primal and dual that makes the definition of a backdoor kind of more interesting or more rich. If you have an infeasible problem, then kind of things are much simpler. You just need to be able to branch on a small set of variables such that you prove that the problem is infeasible. And if you care about feasible instances, then you have to think about, you know, the primal side of things as well. So you have to find the optimal solution and also prove that it is optimal. So for example, in this toy tree, this green node might be this optimal solution, which happens to be a LP relaxation, which is integer. Okay. So at the time, Dilkina et al. Tried to look at kind of carry these results from satisfiability into integer programming and try to look at the time, I believe it was MIPLIP 2003, try to look at those instances and just randomly sample tiny subsets of the variables, call a solver, let it branch only on those variables, and see if it terminates with zero gap, right? And they observed that even with like a simple random sampling scheme, so here this plot shows two sampling schemes, uniform sampling and bias sampling, for this one instance, 10 teams, which you may have encountered from MIPLIP 2003. And what they're measuring here is as you increase the size of the set of variables, what is the probability in a large sample of trials of the search, the solver terminating with a proof of optimality. Okay, so you can see that when the percentage is very small, close to zero, the probability is low, and then it kind of goes up. And the two sampling scheme differ in one basic way. Uniform is just uniform sampling. Bias sampling uses the root LP relaxation solution to make it more likely to sample variables that are more fractional, okay? And so that is one way to kind of direct the sampling process. And they show that it's a bit more likely to find a backdoor with such a sampling scheme. So this was an instance with 1,800 integer variables. And as you got to 20% on the horizontal axis, you could see this probability of finding a backdoor kind of shooting up. So this was the procedure. Of course, a key part of the procedure is evaluating this set, any set of variables. This requires a call to the solver, in which you direct it to only branch on that subset of variables at up to depth, let's say B, where B here is the size of the backdoor. Okay, so for example, in Cplex, you can specify branching priorities, and you can say for these 5 variables, branching priority is 1, for all the rest is 0. So please Cplex, whenever you can branch on any one of these variables I like, prioritize that over others. Even if you're doing strong branching, even if you're doing whatever it is, prioritize these. Once you go deeper in the tree, you don't need to rely on these, and the solver can do whatever it likes. So once you run that, the solver is going to return, and it's either going to have solved the instance or not. And then if it did, then we declare that set of variables B, which is very small again, a backdoor. Okay, so here the perspective up to this point was kind of defining the notion of backdoor for integer programs, going from satisfiability to optimization, and kind of exploring empirically if such things appear. Then a bit after that, Fischetti and Bonacci looked at this problem again, but more from a computational perspective, with the motivation that if you could identify such small sets of variables, then potentially you could speed up the overall solution time by prioritizing branching on them. So they called that suitably backdoor branching. And the key insight there was that for binary problems, there's an equivalence or an equivalent definition for backdoors. So a set of variables, B is a backdoor if for every good fractional vertex of the 0-1 polytope, at least one of the fractional variables for that point is in that backdoor. So you can think of it as a kind of a set covering formulation. You want a small set of variables such that if you were to branch on those, that eliminates the possibility of encountering a suboptimal fractional vertex, okay? So with that formulation, of course, there can be exponentially many such fractional vertices that you want to eliminate. This is where the computational kind of challenges arise. But they proposed, if you want a constraint generation algorithm, which is kind of practical, in which you iterate 3 steps. First, you find a small subset of variables that cover a current data set of fractional LP solutions. So the way you get that is you run a bit of branch and bound. You haven't solved the instance. So by definition, there are some fractional solutions at the nodes. You take those and you say, how do I cover these solutions? Where by covering, we mean the set of variables we pick must cover each solution. There will be at least one fractional variable in the solution in the backdoor set. So once you identify that, you can do that with a set covering formulation. Now you ask the MIP solver to branch on the set B. And if the instance is solved, you found a backdoor. Otherwise, you must have encountered new fractional variables and you want to eliminate those. So you add them to your data set of fractional solutions and you go back to 1. And now you try to cover them. And now you might need additional variables to add to this backdoor set or a different combination of variables. Okay, so this is nice. It works. It's a very clean correspondence for the binary case. Okay, and why do we care about backdoors? There can be many reasons. The one I'm most interested in is kind of from an empirical perspective. The existence of a small backdoor for an instance with many, potentially thousands of variables or tens of thousands of variables tells us something about maybe the intrinsic combinatorial structure in this MIP. If you only need to branch on 5 or 10 variables in a 100,000 variable problem, that should tell us something about the structure of the problem. Maybe it can inform some more theoretical understanding of a given model or a class of models. And of course, computationally, if you could find it efficiently, if you could identify that set, then you can branch on those and maybe get a small branch and bound tree. So we'll come back to that idea. The con of this whole notion of backdoors is, of course, I'm introducing a much harder problem than the original problem because we're now searching kind of in the space of branch and bound trees rather than the space of integer solutions. So it's unclear that defining this problem is of any practical use. And the other thing is that this notion, this definition is quite brittle in the sense that you pick a bunch of variables and they're either a backdoor or they're not. There's really not much in between. And because we expect such objects to be very rare, this kind of tells us that you're searching for a needle in a haystack. So this makes it a bit scary to approach. So part of the motivation of this work is to break some of these barriers and make it easier to assess computationally whether backdoors exist or not for instances that you care about. Okay, so I had already talked about 2 methods, one based on random sampling and the other from Fischetti and Monarchy based on the set covering formulation. There are pros and cons. The random sampling is obviously very easy to implement and parallelize. You just sample a bunch of variables and you ask the solver if they solve the instance or not. But they're also clearly not going to be very efficient, sample efficient, because again, it's a needle in a haystack type problem. Backdoor branching is the principled algorithm. It's been shown in that paper to work quite reasonably well. But the notion of relying on linear programming solutions at the nodes, that can be a bit noisy. So if you attended Ambrose's talk yesterday about exact rational integer programming, you know that the kind of the floating point version of the solver might not always give you something which is truly feasible in the constraints, etc. And actually, Matteo noted that in a different kind of context by saying you shouldn't trust the fractional point. The kinds of fractional point you encounter in a branch and bound depend on all kinds of things, and we know that kind of from performance variability in MIP that you change the ordering of the rows and columns that affects your bases and that affects your optimal LP. And then if you have degeneracy, you might encounter very different trees than you would with another random seed. And so having an algorithm that searches for backdoors based on LP solutions, which may be noisy, might not be kind of the most desirable thing. And so what we would like to do is to design a backdoor search algorithm that simultaneously achieves the following. It's more sample efficient than random sampling. So that one is obvious because random sampling is immediate. So it should be an algorithm that kind of improves as you give it more iterations, more time. It should be able to leverage partial reward signals from failed trials. So this is tied to the notion of definition of a backdoor. If I branch on, say, 5 variables and the solver has not is not done, should I just declare that this combination of variables is bad, or should I look at some other partial metric of performance so that I can assess that this set of variables may not be a backdoor, but it's better than some other set of variables of equal size? Okay, so this ties a lot into estimating the search tree size that Gregor talked about, and I'll come back to that. And last, we want whatever algorithm we design to be flexible and amenable to improvements via machine learning. Obviously, it's something I personally care about, but I think this is a place where machine learning can potentially play a very big role in helping identify such sets of variables. So we want the algorithm to be flexible, and you'll see what I mean when I describe it. And so the overall procedure is going to look like this. We have one MIP instance, some backdoor size we care about K. Think of this as being just a constant, something very small, and some iteration or time limit. And we're going to repeat the following T times. We're going to suggest a set of variables, let's call it BT, where T refers to the iteration. This set has K variables in it. It goes to a solver. The solver tells you something about how good your suggestion BT did. So in the most kind of binary case, it will tell you this is a backdoor, I'm done, or this is not. But we will want something which is a bit more kind of that interpolates between the two. And then once you've collected that reward for the suggested backdoor BT, you want to go back and suggest BT plus 1, and you want to keep doing that until you exhaust the limit. And hopefully by then you will have found something which is good. Okay, so the reward signal is a very important component of this. And Gregor yesterday talked about various metrics that you can use to quantify tree search completion. So here I'll use one of them, which is tree weight, but the approach I'm going to talk about doesn't rely on that necessarily. It's just one that makes sense. And tree weight says the following. If you give me any tree, what we can do is we can look at the nodes on the frontier, look at the closed nodes, i.e. ones that were fathomed by bound or infeasible or that have integer relaxations, look at their depth, and then look at how many potential integer solutions we've eliminated by reaching those fathomed nodes, okay? So obviously, if all those nodes at the frontier were fathomed, then we'll have completed 100% of the search. In this case, for example, if you had 10 variables, then the tree weight is something like 2 to the minus 3 plus 2 to the minus 2. So it tells you that in the binary case, you've eliminated 3 out of 8 of all possible 0-1 assignments. Okay, so this is also not a perfect measure, but it is a better measure than saying this is a backdoor or this is not. So this gives you something in between. So if I branch on 5 variables or 3 variables and my tree weight is close to 1, even though it's not a backdoor, that's quite good. Maybe there's one node I need to explore further by branching on other variables, but that's better than having 10 open nodes at a very kind of depth close to the root. So this is one metric that we can use to quantify the quality of any suggested set of branching variables. So next, we're going to plug this notion of reward metric, this tree weight, into a search scheme. The search scheme is going to be based on Monte Carlo tree search. That's why there's lots of trees in the stock. So Monte Carlo here is referring to the typical like Monte Carlo simulation approach. And tree search refers to structuring the space of possible backdoors, these small sets of variables, into a tree structured object, and using that to navigate the space, okay? And you will want any algorithm to kind of know how to balance exploration and exploitation, how to not just do like breadth first search or depth first search. It should kind of rely on these reward signals to focus its efforts on promising regions. And Monte Carlo tree search is kind of a very general formalism. It's been used to, you've probably heard of it in the context of AlphaGo and AlphaZero from DeepMind, et cetera. So it's been used a lot in combinatorial type problems, especially in games. So here, how does this map to the backdoor setting? The tree that we're going to search over represents the search space, which is the set of all possible size k permutations of the variables. And again, k here is very small. And the depth of the nodes is going to refer to the priority we're going to give to branching on a given variable. So variables at the level 1, for example, xj here, will have higher priority than xk, which in turn will have higher priority than xl, and so on and so forth. Okay, the depth of the maximum depth of this tree is going to be k, because you have at most k variables, and we're going to try to grow this tree in a way that just does not, allows us to kind of converge to good backdoors. The branching factor is obviously the number of integer variables that you're searching over. So this can be quite large. So this is not a binary tree like in branch and bound for MIP. And each of these nodes is gonna contain some kind of reward estimate, which measures the quality of the backdoors that we've seen in the subtree rooted at a given node, okay? The Monte Carlo simulation part comes from not expanding this tree fully, so not going to depth k every time, but rather you might go to depth 2. So for example, you might go down the path from the root, pick x2 and x6. Let's say k is 5, rather than building a path by adding 3 more variables, you might just sample a few, a few sets of 3 variables and add them to the set x2, x6, run the solver on that and get some reward. So this is the Monte Carlo, the kind of simulation or stochastic aspect of this procedure. And this procedure can be implemented in a way that it's exact, okay, that's complete. Given enough time, it will explore all possible combinations and return the best one. But in practice, it's very rare that you actually run it this long, unless you have a very tiny set of variables. So the overall procedure looks like this. At any point in time, you have this Monte Carlo tree. You will traverse the tree from the root to one of the leaf nodes, and you should do so balancing exploration and exploitation. So you shouldn't keep hammering on the same node if it's giving you bad rewards, and you should kind of diversify. You get to a node, you might expand it by creating a new child of it. And then you will need to simulate by completing the set of variables until you get to a size k set. And now you run the solver. It tells you something about the tree weight with this reward function. And then you do some kind of backpropagation. You tell the parents of the node from which you simulated what you observed. So this is referred to here as backpropagation. And then you go to the next iteration, you repeat, you visit other nodes, so on and so forth. There are many design choices here, and so far what we've done is kind of the most. Sorry,
2 minutes. 2 minutes plus time for questions.
Okay, thank you. There are many design choices, a very algorithmically kind of rich space of things to do. So far, we've done some of the basic choices typical when doing Monte Carlo tree search with large accent spaces. So to select nodes, we use this upper confidence trees or UCT, which is a formula that balances the rewards you've seen with the amounts of visits you've given to a node. So you don't want to over visit and you don't want to visit things that are useless. And we can also combine that with MIP specific information like pseudo costs to kind of bias the search. And we don't expand the tree fully because the branching factor can be huge. We use a kind of a progressive technique. We use random sampling to simulate these sets of backdoors. And we use a max backup for backpropagation, meaning for every node, we know what was the best highest three-weight solution we've seen in its subtree. And so we've evaluated this on a subset of MIPLIP 2017, the benchmark set. We looked at the mixed binary subset. We've looked at backdoors of size 8, and we've run this procedure and another random sampling procedure for 5 hours and tried to see, do we find things that are very close to being a real backdoor that solve the instance to near kind of global optimality? So do these things even exist? So here what you're looking at is a histogram of these three weights. So 1 means it's a backdoor, 0 means it's very bad. And you can see it's kind of bimodal. There are many instances that don't seem to have small backdoors, but there are quite a few that have something in the 0.8 to 1 range, meaning you branch only on 8 variables and you almost solve the problem, even when it has bazillion variables. And the approach that I've discussed here, MCTS, basically vastly outperforms a random sampling procedure. And you can see that's here for one instance. We look at time and we look at kind of the best backdoor we've encountered, and you see blue converging in a kind of much nicer way. And this is kind of consistent behavior. And if you compare the best solution found through random sampling versus Monte Carlo tree search, Monte Carlo tree search is kind of consistently better, finding much better solutions. And we find that also the success of this procedure doesn't depend on there being a small number of variables. So even when there's many fractional variables in the root LP, these approaches can find small sets that give you almost a complete search tree. And you can take these small backdoors and run them with CPLEX, tell it to branch, prioritize branching on those. And we've done that on a small subset and observed a reduction in the total number of nodes in the branch and bound tree. So actually, even if you take 8 variables, which are close to being a backdoor, and you just prioritize branching on that, you can do better than the default solver. But obviously, this doesn't factor in the time taken to find the backdoors themselves, which is kind of an avenue for future exploration. So with that, I'll thank you for your attention, and I'm happy to take any further questions here on Slack.
Fantastic, thank you. Any questions in the Q&A, please type them out. I'll just start off and ask, can you solve similar instances using the backdoor for a related instance? It's like if I perturb a problem,
you could if the identities of the variables are kind of similar, right? So x2 means the same thing, and maybe some coefficients have changed. We haven't tried that, but that's actually an interesting thing. I suspect that if the change is not too drastic, they might kind of transfer to some extent.
Okay, yeah. And we have a question, does it make sense to explore backdoors for MIPS arising from particular common core optimization problems?
Yes, it does. So we're about to put this out, and we have some results on a structured set of problems where kind of things are more homogeneous. So you can observe these backdoor patterns in a bit more, in a cleaner way than on MIPLIP. So yeah, it definitely does.
Great. Can we take one more question from the audience? And I guess I'll also ask, does this mean you can kind of like restrict integrality to only a few variables and then mostly solve the problem?
So it's close to that. If you have an infeasible problem, then it reduces to that. So if you restrict integrality to only the backdoor set, and then you get an infeasible instance, then they're a backdoor set. But it's tricky if you care about the primal side, because there's you have to take care of finding integer solutions for the original integer set.
Yeah. Okay, interesting. Let's see, one more question. Let's see, it says, reminds me of bandit learning methods, which use the formula to prioritize some branches. Have you checked them?
Yes, so yeah, MCTS is one variant of bandit methods for kind of tree structured domain. So indeed, that's kind of essentially what's going on.
All right.
Yes, thank you.
Well, great, thanks. We will
All right.
go on to the next speaker.
Thank you, everybody.